Everyone, this is an audio recording for the visually impaired student from the book Pradeep Physical Chemistry, Volume 2 by Dr. S.C. Khetrapal. Thermodynamics Part 2. Introduction. Need for the second law and different statement of the law. The first law of thermodynamics had certain serious limitations. To overcome this limitation, a strong need was therefore felt to introduce another law called the second law of thermodynamics. A few limitations of the first law and the consequences, some definition given to the second law are briefly given below. First is a major limitation of the first law of thermodynamics is that it may really indicate that in any process there is an exact equivalence between the various forms of energy involved, but it provides no information concerning the feasibility of the process, is that whether the process is possible or not. For example, the first law does not indicate whether heat can flow from a cold end to a hot end or not. All that it tells is that if this process occurred, the heat energy gained by one end would be exactly equal to that lost by the other end. Similarly, the first law does not tell whether a gas can diffuse from low pressure to high pressure or water can itself run uphill, etc. The second law supply answer to the above question by stating that all spontaneous process like the flow of heat from hot end to cold end, diffusion of gas from high pressure to low pressure, or the flow of water down a hill, etc. are thermodynamically reversible. First definition. The term spontaneous process used in the above definition means a process which can take place without the help of any external agency. All natural processes, some of which are mentioned in the definition above, are spontaneous process. Above it may be mentioned here that the term spontaneous does not give any idea of the rate of process, is that whether the process takes place fast or slowly. All that it implies is that a process can occur without the help of an external agency. Second definition is the first law state that when heat is converted into work, the work obtained is equivalent to the heat absorbed. However, it has been seen from experience that the heat absorbed cannot be completely converted into work without leaving some change in the system or the surrounding. For example, the heat produced in a locomotive is not fully utilized in running the train. A part of it is it you lost to the surrounding or wasted in overcoming the friction. Hence, the second law is also stated as follows. The complete conversion of heat into work is impossible without leaving some effect elsewhere. Second definition. Beside the above definition, a number of other definitions have also been given to the second law of thermodynamics. The two important ones are: it is impossible to construct a machine functioning in cycle which can convert heat completely into the equivalent amount of work without producing some change elsewhere. Third definition. Without the use of an external agency, heat cannot by itself pass from a colder to a hotter body. Fourth definition. The term functioning in cycle is introduced in the above definition to indicate that the machine must return to its original state at regular intervals so that it can function continuously. Further, it may be recalled that in an isothermal reversible expansion of an ideal gas, delta U is equal to 0, so that Q is equal to W, is that work done is exactly equal to the heat absorbed by the system. In other words, in this process, heat is completely converted into work. However, it is important to observe that this conversion is occupied by an increase in volume of the gas so that the system has undergo a change. A number of other definitions have also been given to the second law of thermodynamics, which we will come across in the succeeding section of this chapter. The fraction of the heat absorbed by a machine that it can transform into work is called the efficiency of the machine. Thus, if Q is the heat absorbed and W is the work done, then the efficiency of the machine is given by neta is equal to W by Q. The machine used for the conversion of heat into work is called heat engine. In order to bring about this conversion, the engine absorbs heat from a heat reservoir at a higher temperature called the source, convert a part of it into work, and return the remainder to the heat reservoir at a lower temperature called the sink. Carnot cycle and its efficiency. In order to calculate the efficiency of any heat engine, Sadi Carnot in 1824 devised a technique called Carnot cycle. A cycle is a process in which a system returns to its original state after a number of successive changes. A process conducted in this manner is called a cyclic process. The engine chosen for Carnot, called Carnot engine for the purpose of the calculation of the efficiency, was a hypothetical one and cannot be achieved in actual practice. It was selected because it could be subjected to simple thermodynamic treatment. It consists of a cylinder containing 1 mole of an ideal gas as a working substance and fitted with frictionless piston so that all the operation in the cycle are carried out reversibly. For this reason, it is also called reversible heat engine. The cylinder is supposed to be insulated on all sides except at the bottom so that heat can flow to or from the system only through the bottom. Further, it is supposed that there are two heat reservoirs, one at a higher temperature T2 called the source and the other at a lower temperature T1 called the sink. If some operation is carried out by placing the cylinder in the source or the sink, it can exchange heat with it and hence the temperature remains constant so that the process is isothermal. On the other hand, if during an operation the cylinder is placed on an insulating material, no heat exchange can take place between the system and the surrounding and hence the process is adiabatic. The Carnot cycle consists of 4 different operations which can be represented on a pressure volume diagram, sometimes called an indicator diagram, as shown in figure 2.1. These operations are carried out as shown in figure 2.2 and are briefly described below. Alternatively, the cylinder may have conducting wall as well as the bottom and the source, and the sink may be two thermostat. For carrying out isothermal process, the cylinder may be placed in the thermostat. For carrying out adiabatic process, the cylinder may be placed in perfectly non-conducting jacket. Isothermal expansion. The cylinder containing 1 mole of the ideal gas occupying a volume V1 is placed in contact with the source heat reservoir at temperature T2. The gas absorbs heat Q2 from the source and expands isothermally and reversibly till its volume has increased to V2. The path of the process is represented by the isothermal curve AB. Since the gas is ideal, the work done W1 by 1 mole of the ideal gas will be given by minus W1 is equal to RT2 ln of V2 by V1. Further, for an ideal gas, the work done is given equal to the heat absorbed Q2 so that minus W1 is equal to Q2, which is equal to RT2 ln of V2 by V1. Here W1 have been taken as negative and Q2 as positive by the latest SI convention of signs. Adiabatic expansion. The cylinder is now removed from the source and placed in perfectly insulating material so that the gas now expands adiabatically and reversibly. Work is done in the expansion, but since no heat enter or leave the system, the temperature must fall. The reversible adiabatic expansion is continued till the temperature has fallen to T1, which is the temperature of the sink. Suppose the corresponding volume becomes V3. The path is shown by the adiabatic curve BC. The work done W2 will be given by minus W2 is equal to CV T1 minus T2, which is equal to minus CV T2 minus T1, where CV is the heat capacity of the ideal gas. Here again W2 is negative by the usual convention of sign. Isothermal compression. The cylinder is now removed from the insulating material and placed in contact with the sink is at the heat reservoir at the lower temperature T1. The gas is compressed isothermally and reversibly till the volume decreased from V3 to V4. The process is represented by the path CD in figure 2.1. The work done is taken as positive by the usual convention of sign and hence will be given by W2 is equal to RT1 ln of V4 by V3. During the operation, an amount of heat Q1 exactly equal to W2 will returns to the sink at T1 is that heat has been given out by the system. Using the appropriate convention of sign, Q1 will be negative and W3 will be positive so that minus Q1 is equal to W3, which is equal to RT1 ln of V4 by V3. Adiabatic compression. The cylinder is now removed from the sink and placed again on the insulating material. The gas is then compressed adiabatically and reversibly along dA till the initial state A is regained. The temperature of the gas rises from T1 to T2. The work done is positive by the convention of sign and will be given by W4 is equal to CV T2 minus T1. As a result of which these four operations, the system has returned to its original state so that a reversible cycle has been completed. The work done W given by the system will be given by W is equal to minus W1 plus minus W2 plus W3 plus W4, which is equal to RT2 ln of V2 by V1 minus CV T2 minus T1 plus RT1 ln of V4 by V3 plus CV T2 minus T1. This is the equation. Which is equal to RT2 ln of V2 by V1 plus RT1 ln of V4 by V3, equation 8. Since V1 and V4 lie on an adiabatic curve and V3 and V2 lie on another curve, it follows that V4 by V1 raised to power gamma minus 1 is equal to T2 by T1, equation 9, and V3 by V2 raised to power gamma minus 1 is equal to T2 by T1. This is equation 10. Comparing equation 9 and 10, we get V4 by V1 gamma minus 1 is equal to V3 by V2 raised to power gamma minus 1, or V4 by V1, which is equal to V3 by V2, or V4 by V3 is equal to V1 by V2. Putting this value in equation 8, we get is equal to RT2 ln of V2 by V1 plus RT1 ln of V1 by V2, which is equal to RT2 ln of V2 by V1 minus RT1 ln of V2 by V1, which is equal to RT2 minus T1 ln of V2 by V1. This is equation 12. Dividing equation 12 by equation 2, we get W by Q2 is equal to T2 minus T1 divided by T2, which give the efficiency of the Carnot cycle or engine. Carnot theorem. From equation 13, it is clear that the efficiency of a reversible heat engine depend only upon the temperature of the source, and the source and is independent, and the sink end is independent of the nature of the working substance. Another important observation to be made from the above derivation is that the work done in the cycle is only the one involved in the isothermal operation, because the work done in the adiabatic operation 2 and 4 cancel one another. Further, as discussed earlier, the work done in a reversible isothermal expansion from A to B is maximum, whereas the work done on the gas during the reversible isothermal compression from C to D is minimum. Hence, the total work done by the system is that the reversible heat engine or Carnot engine is maximum for the specified condition, and therefore the efficiency is maximum. The result that followed from the Carnot cycle as derived and discussed in equation 18 above is called the Carnot theorem. It may be stated as follow. The efficiency of a reversible heat engine depend only on the temperature of the source and the sink, and is independent of the nature of the working substance. In other words, all reversible heat engine working between the same two temperature have the same efficiency. Further, it states that the efficiency of a reversible heat engine is maximum for the given temperature. Since the quantity T2 minus T1 divided by T2 is always less than unity, the efficiency of the heat engine is thus always less than unity. In view of the above discussion, the second law of thermodynamics is sometimes defined as follow. A heat engine absorbs a certain amount of heat from the source, convert a part of it into work, and return the rest to the sink. In other words, it is impossible to convert heat completely into work. Further, combine equation 2, 5 and 8, we get W is equal to Q2 minus Q1 is that the net work done by the system is equal to the net heat absorbed by the system. Putting the value of W in equation 13, we get Q2 minus Q1 divided by Q2 is equal to T2 minus T1 divided by T2. Hence, the efficiency of a heat engine may be given by any one of the following expression. Neta is equal to W by Q2, which is equal to Q2 minus Q1 divided by Q2, which is equal to T2 minus T1 divided by T2. Thus, This result derived for a reversible Carnot cycle leads to the introduction of a new thermodynamic term called entropy as discussed in session 2.5. Thermodynamic scale of temperature. From our earlier study, we are familiar that a thermometer is constructed most commonly by taking suitable amount of mercury in a glass bulb at the end of a capillary tube and marking 0 when it is placed in contact with the ice and making 100 when it is placed in boiling water. The length between the 2 points is divided into 100 equal part called degrees. The scale of temperature thus obtained is called Celsius scale of temperature. However, because different liquid expand to different extent, is that their coefficient of expansion are different and also they do not expand uniformly over a given range. Thermometer constructed by using different liquid will show different numerical values of temperature between their fixed point. For example, a body may show a temperature of 28.7 degrees Celsius with mercury thermometer but may show 28.8 degrees Celsius with an alcohol thermometer. The problem was solved by a study of properties of gases. It was found that an ideal gas or a perfect gas ceases to exist at a temperature of minus 273.15 degrees Celsius. This temperature was called 0 degree absolute. The scale developed on this basis is called perfect gas temperature scale and is found to be independent of the ideal gas taken. However, based on the efficiency of a reversible heat engine, Lord Kelvin was the first to develop a scale of temperature that was independent of the nature of the gas taken in the heat engine. This scale of temperature is called thermodynamic scale of temperature or Kelvin scale of temperature. It is found to be identical with the ideal gas temperature scale. The basis of the development of this scale is briefly described below. Suppose there are two constant temperature heat reservoirs, one acting as a source and the other as a sink, and a reversible heat engine operate between them. The temperature of each reservoir on the new scale may be taken as proportional to the quantity of heat absorbed from the source and the heat lost to the sink, both of which can be measured. If Q2 is the heat transfer from the source is at heat reservoir at higher temperature and Q1 is the heat transfer in the sink reservoir at lower temperature, then if their temperature on the thermodynamics or Kelvin scale are represented by theta 2 and theta 1 respectively, we shall have Q2 by Q1 is equal to theta 2 minus theta 2 divided by theta 1, that is equation 1. Thus, this ratio of two temperature that has been defined in a manner independent of the nature of the thermometric substances. Taking the reciprocal of both sides of equation 1 and subtracting the result from unity, we get 1 minus q1 by q2 is equal to 1 minus theta 1 by theta 2, or q2 minus q1 divided by q2 is equal to theta 2 minus theta 1 divided by theta 2. Putting theta 1 is equal to 0 is at 0 of the new scale, we get q2 minus q1 divided by q2 is equal to 1. This implies that 0 on the Kelvin scale is the temperature of the sink for the reversible heat engine whose efficiency is unity, is that which is capable of converting heat completely into work. But from equation 14 page number 86 it may be seen that it is possible only at absolute 0 on the ideal gas scale of temperature. This leads to the conclusion that the Kelvin scale and the gas scale are identical provided the gas is ideal. The temperature on the thermodynamic scale are therefore expressed in terms of degree Kelvin. Further, it has been found that if the lower fixed temperature is taken as equal to that of triple point of water with 273.16 Kelvin, then Kelvin is exactly equal to Celsius degree. For this reason, the temperature on the absolute scale in which the melting point of ice is taken as 273.16 degrees Celsius degree is often referred to as a degree Kelvin. It may be concluded that thermodynamic scale of temperature as defined on the basis of second law of thermodynamics is more basic than that based on the ideal gas because any fluid can be used. However, the ideal gas scale is more practical for laboratory use. Concept of entropy. Entropy as a state function. For a reversible Carnot cycle, Working between temperature T2 and T1, it has been seen that Q2 minus Q1 divided by Q2 is equal to T2 minus T1 divided by T2. That is equation 1, where Q2 is the heat absorbed isothermally and reversibly at temperature T2 and Q1 is the heat lost isothermally and reversibly at temperature T1. The above equation may be simplified as 1 minus Q1 divided by Q2 is equal to 1 minus T1 divided by T2, or Q2 by T1 is equal to Q1 by T1, that is equation 2, or Q by T is equal to constant. Thus we conclude that heat absorbed or lost isothermally and reversibly divided by the absolute temperature at which the heat is absorbed or lost in a constant quantity for a particular system. Further, in equation 2, Q2 is the heat absorbed at temperature T2 and Q1 is the heat lost at temperature T1. If Q1 were the heat absorbed at temperature T1, equation 2 would be rewritten as Q2 by T2 is equal to minus Q1 by T1, or Q2 by T2 plus Q1 by T1 is equal to 0. Is that summation of Q by T is equal to 0? That is equation 3. Now consider an irreversible cycle ABA. It may be regarded as being made up of a number of Carnot cycle drawn across the diagram as shown in figure 2.3. Starting from A and going through all the cycles successively from A to B, it can be shown that all paths inside the closed curve ABA cancel each other, leaving only the zigzag path, which is almost the same as the path ABA of the reversible cycle. By making each Carnot cycle smaller and increasing their number, it can be made to correspond more closely to ABA. The reversible cycle can therefore be regarded as being made up of an infinite number of Carnot cycles. For each of these cycles, we have summation of Q by T is equal to 0 as above. Hence, for an infinite number of Carnot cycles, summation of del Q by T is equal to 0, where del Q is a very small quantity of the heat absorbed at temperature T during the small isothermal change of the reversible process. Further, the above term may be divided into two parts, one for the path A to B and the other for the back path B to A. The summation of del Q by T is equal to summation A to B del Q by T plus summation B to A del Q by T is equal to 0, or we may write summation A to B del Q by T is equal to minus summation of B to A del Q by T, or Q by T A to B is equal to minus Q by T B to A. This implies that the total value of the quantity Q by T for the path A to B is equal to the total volume value of the quantity Q by T for the reverse path B to A. Hence, it may be concluded that the quantity Q by T is a state function, is that its value depend only on the initial state A and the final state B and is independent of the path. Obviously, Q by T is the change in the value of the quantity for a function having some definite value at A and B depending on the value of pressure, volume and temperature. This quantity or the function is called entropy and is usually represented by the symbol S. Thus, if SA is the value of the entropy at A and SB is the value at B, then we must have Q by T is equal to SB minus SA is equal to del S, where del S represent the total change in entropy in going from the initial state A to the final state B. Hence, entropy may be defined as a state function, the change in the value of which from the initial state to the final state is change to the quantity Q by T, is that the total heat absorbed reversibly and isothermally in going from the initial state to the final state divided by the absolute temperature at which the heat is absorbed. From equation 6, the entropy change may be defined directly as the quantity of heat absorbed isothermally and reversibly divided by the absolute temperature T at which the heat is absorbed. It is important to note that as entropy is a state function, therefore the value of entropy change during a process should not depend on the path, is that whether the heat is absorbed reversibly or irreversibly during the process. However, since the derivation of the above result is based on Carnot cycle in which the heat is absorbed reversibly, therefore the expression 6 for the entropy change is valid only when the heat is absorbed reversibly. Thus, it is better to use the symbol del Q reversible REV in place of Q. The expression 6 may therefore be written as delta S is equal to Q REV divided by T. Further, as entropy as a state function, a small change in its value can be represented by ds. Hence, we may write ds is equal to Q reversible divided by T unit of entropy. From the expression delta S divided by delta S is equal to Q by T, it is obvious that the unit of entropy will be calorie per degree if heat is expressed in calories. Therefore, entropy is an extensive property. It is therefore important to mention the quantity of the substance involved. It is usually expressed for 1 mole of the substance. Hence, the entropy unit are calorie per degree per mole. If heat is measured in joule, the unit of entropy will be joule per degree per mole. Entropy change in a reversible process. Suppose a process occur under completely reversible condition is that the heat is absorbed by the system reversibly and the heat is lost by the surrounding also reversibly. If Q reversible is the heat absorbed by the system reversibly, then the heat lost by the surrounding will also be Q reversible. If the process takes place isothermally at the absolute temperature T, then first is entropy change of the system will be given by delta S system is equal to Q reversible by T. Entropy change of the surrounding will be given by delta S surrounding is equal to minus Q reversible divided by T. Then total entropy change for the combined system and the surrounding will be delta S system plus delta S surrounding is equal to Q reversible by T minus Q reversible by T is equal to 0. Thus we may conclude that in a reversible process the net entropy change for the combined system and the surrounding is 0 is that there is no net change in the entropy. Entropy change in an irreversible process. If any part of the process is irreversible, the process as a whole is irreversible. Suppose that the total heat lost by the surrounding is Q irreversible. This heat will be absorbed by the system, but the entropy change of the system does not depend on the heat actually absorbed, but it depends on the heat absorbed reversibly on the quantity Q reversible. Thus, if the heat is absorbed isothermally by the system at the absolute temperature T, the entropy change of the system will be delta S system is equal to Q reversible divided by T. That is equation 1. Further, suppose that the loss of heat Q irreversible by the surrounding takes place infinitesimally slowly is that reversibly and in isothermally at the temperature T, then the entropy change of the surrounding will be given by delta S surrounding is equal to minus Q irreversible divided by T. The total entropy change for the combined system and the surrounding will therefore be delta S system plus delta S surrounding is equal to Q reversible by T minus Q irreversible by T. That is equation 3. Now we know that the work done in a reversible process is the maximum work is that Q reversible is greater than W reversible is greater than W irreversible. That is equation 4. Further, as the internal energy U is the state function, the value of delta U is same whether the process is carried out reversibly or irreversibly. Hence, delta U is equal to Q reversible minus W reversible, which is equal to Q irreversible minus W irreversible. That is equation 5. Combining result 4 and 5, we conclude that Q reversible is greater than Q irreversible. Is that Q reversible by T greater than Q irreversible by T? That is equation 7. Or Q reversible by T minus Q irreversible by T is greater than 0. Combine this result with the result given in equation 3, we observe that delta S system plus delta S surrounding is greater than 0. That is equation 9. Thus we may conclude that in an irreversible process the entropy change for the combined system and the surrounding is greater than 0 is that an irreversible process is accompanied by an net increase of entropy. Since all spontaneous processes are thermodynamically irreversible, first definition of second law of thermodynamics, it may state that all spontaneous processes are accompanied by a net increase of entropy. This is also one of the very common statement of the second law of thermodynamics. This result for the entropy change in a reversible process and that is an irreversible process may be combined together and put in the form delta S system plus delta S surrounding is greater or equal to 0, where the sign equal to stand for the reversible process and the sign greater than for the irreversible process. The exact calculation of total entropy change delta S total during an irreversible process is that when heat flow from a body B at a higher temperature T2 to a body A at lower temperature T1, when brought in contact with it may be carried out as follows. Suppose the heat lost by the body B is represented as Q reversible. The flow of heat may be allowed to take place infinitesimally slowly so that it is absorbed by the body A reversibly and isothermally at which may be represented as Q reversible. The entropy change of the body B also depend only on Q reversible. Hence, entropy change of body B is equal to minus Q reversible by T2. Entropy change of body A is equal to plus Q reversible by T1. Minus sign indicate decrease in entropy, while positive sign indicate increase. Delta S total is equal to minus Q reversible by T2 plus Q reversible by T1 is equal to Q reversible 1 by T1 minus 1 by T2. The combined system and the surrounding is sometimes called an isolated system. The result derived in this session are thus for the isolated system. Negative sign with W has been used as it is the work of expansion. Clausius inequality. As discussed above, for the an isothermal process, the result given in equation 9 may be rewritten as delta S system plus delta S surrounding is greater than 0, that is equation 1, or delta S system greater than minus delta S surrounding. Also for equation 2 we have delta S surrounding which is equal to minus Q by T, that is equation 3. Putting this value in equation 2 above, we get delta S system is greater than Q by T. For small changes, the above equation may be written as delta S system ds system is greater than minus ds surrounding, that is equation 5, or ds system is greater than delta Q by T. dq by t. Expression 4 and 6 are called Clausius inequality. These equations show that irreversible processes are accompanied by increase of entropy. This is further illustrated with the help of the following two examples of irreversible process. First is the spontaneous expansion. A part, irreversible adiabatic expansion. Suppose the system undergoes irreversible adiabatic change, then dq is equal to 0. Hence, by Clausius inequality, ds system is greater than 0. The entropy of the system has increased further as dq is equal to 0. Part A, irreversible adiabatic expansion. Suppose the system undergo irreversible adiabatic change, then dq is equal to 0. Hence, by Clausius inequality, ds system is greater than 0 is that the entropy of the system has increased further as dq is equal to 0. This means that no heat is transferred into the surrounding. Thus, ds surrounding is equal to 0. Hence, total entropy change ds total is equal to ds system plus ds surrounding, which is equal to ds system. But ds system is greater than 0 as explained, hence ds total is greater than 0. Second is the irreversible isothermal expansion. We know that when a perfect gas expands isothermally, its internal energy remains constant, is that du is equal to 0. Hence, according to first law of thermodynamics, du is equal to dq plus dw. dq plus dw is equal to 0, or dq is equal to minus dw, that is equation 7. If the gas expands freely into vacuum, no work is done, so that dw is equal to 0. Substituting in equation 7 gives dq is equal to 0. Hence, by Clausius inequality, ds system is greater than 0. Further, as dq is equal to 0, it is implies that ds surrounding is equal to 0. Hence, the total entropy change as in the above case is that ds total is greater than 0. Second is the spontaneous cooling. Suppose heat is transferred from one system at a higher temperature T2 called the source to another system at a lower temperature T1 called the sink. If heat dq leaves the source and enter the sink, entropy change of the source is minus dq by T2, entropy change of the sink plus dq by T1. Total entropy change ds total is equal to dq by T1 minus dq by T2, that is equal to dq1 by T1 minus 1 by T2. As d1 is very greater than t1, ds total is equal to positive, is that cooling, transfer of heat from hot body to cold body, is accompanied by increase of entropy. Entropy change of the universe. Since all spontaneous processes occurring in nature are thermodynamically irreversible, these are accompanied by increase of entropy as discussed in session 2.7 above. Hence, it may be concluded that the entropy of the universe is continuously increasing. This result is sometimes taken as another statement of the second law of thermodynamics. Thus, the main ideas of the first and the second law of thermodynamics may be summed up in the following statement. The energy of the universe is constant, whereas the entropy of the universe is continuously increasing and tends to a maximum. Entropy change for an ideal gas with the change in pressure, volume and temperature. Consider 1 mole of an ideal gas enclosed in a cylinder fitted with frictionless piston. If an infinitesimally small amount of heat del Q reversible is supply to the system reversibly and isothermally at the temperature T, then the entropy change accompanying the process will be given by ds is equal to del q reversible divided by T. According to first law of thermodynamics, for an infinitesimal process, del q is equal to du minus del w. If the process is carried out reversibly, equation 2 may be written as del q reversible is equal to du minus del w. Therefore, if the work is restricted to the work of expansion, as is usually the case for processes considered in chemical thermodynamics, then minus del w is equal to pdv. That is equation 4, where dv is the small increase in the volume and P is the pressure of the system, which is very nearly equal to the external pressure because the process is carried out reversibly. Putting the value of del W from equation 4 in equation 3, we get del Q reversible is equal to du plus PdV, that is equation 5. Substituting this value in equation 1, we get ds is equal to du plus PdV divided by T, or it may be written as TdS is equal to du plus PdV. Now for 1 mole of an ideal gas, we know that Cv is equal to du by dt and du is equal to Cv dt. That is equation 7, where Cv is the molar heat capacity at constant volume and PV is equal to RT, is that P is equal to RT by V, ideal gas equation, and that is equation 8, where V is the volume of the system at temperature T and pressure P, and R is the gas constant. Putting this value du and P from equation 7 and 8 in equation 6, we get TdS is equal to Cv dt plus RT by V into dV, or ds is equal to Cv dt by T plus R dV by V, that is equation 9. Or if the volume changes from V1 to V1 to V2, then the temperature changes from T1 to T2, then the entropy change accompanying the complete process will be given by ds limit tending to S1 to S2, which is equal to Cv dt by T limit tending T1 to T2 plus R dV by V limit tending V1 to V2. That is equation 10. Assuming that Cv remains constant in the temperature range T1 to T2, equation 10 may be written as integration of ds, where limit tend S1 to T2, which is equal to Cv integration of dt by T, where limit tends T1 to T2 plus R integration of dV by V, where limit tends V1 to V2, or delta S is equal to Cv ln of T1 by T2 by T1 plus R ln of V2 by V1, that is equation 11. This is an expression for the calculation of entropy change of 1 mole of an ideal gas accompanying a process when temperature changes from T1 to T2 and the volume changes from V1 to V2. Further, for 1 mole of an ideal gas, we may write P1 V1 is equal to RT1 for the initial state, that is equation 12, and P2 V2 is equal to RT2 for the final state, that is equation 13. Dividing equation 13 by equation 12, we get P2 V2 divided by P1 V1 is equal to T2 by T1, or V2 by V1 is equal to T2 P1 divided by T1 P2. Putting this value in equation 11, we get delta S is equal to Cv ln of T2 by T1 plus R ln of T2 P1 divided by T1 P2. Further, we know that Cp minus Cv is equal to R, or Cv is equal to Cp minus R. Putting this value in equation 15, we get delta S is equal to Cp minus R into ln of T2 by T1 plus R ln T2 P1 divided by T1 P2 is equal to Cp ln of T2 by T1 minus R ln of T2 by T1 plus R ln of T2 by T1 plus R ln of P1 by P2, or delta S is equal to Cp ln of T2 by T1 plus R ln of P1 by P2. This is an expression for the calculation of the entropy change of 1 mole of the ideal gas accompanying a process when temperature changes from T1 to T2 and the pressure changes from P1 to P2. Entropy change of an ideal gas in different processes. Equation 11 gives the entropy change for 1 mole of the ideal gas when temperature and pressure are variable. Similarly, equation 16 gives the entropy change of 1 mole of the ideal gas when temperature and pressure are variables. These equations are modified if condition of constant temperature, pressure or volume are imposed. For example, first is if temperature is kept constant for isothermal process T1 is equal to T2. Equation 11 and 16 are reduced to delta S is equal to R ln of V2 by V1 is equal to R ln of P1 by P2. Alternatively, this expression can be derived directly as follows: ds is equal to q reversible by T with minus W max is equal to Q reversible is equal to nRT ln of V2 by V1, that is equation 19, is equal to nRT ln of P1 by P2, that is equation 20. Substituting the value of Q reversible from equation 19 and 20 in equation 18 and putting n is equal to 1 for 1 mole of the ideal gas, we get the resulting equation in equation 17. If the pressure is kept constant for isobaric process, P1 is equal to P2, equation 16 is therefore modified to delta S is equal to Cp ln of T2 by T1. If volume is kept constant for isochoric process, V1 is equal to V2, then equation 11 is written, therefore reduced to delta S is equal to Cv ln of T2 by T1. Note carefully that all the expression derived above for the calculation of entropy change ds involved natural logarithms. Since logarithms table commonly used r to the base 10, in applying this formula, in x has to be first replaced by 2.303 log x, where x is quantity like T2 by T1, V2 by V1, etc. Further, note that if a gas expands reversibly but adiabatically, then as for such a process, Q reversible is equal to 0, therefore delta S is equal to 0. Entropy change during physical change, phase change. A change of phase occur in any one of the following changes: when solid melt, or conversely when a liquid freezes. Second is when a liquid evaporate, or conversely when a gas condenses. Third is when one crystalline form changes into another. When the change of the phase commences, the temperature remains constant till the change of the phase is completed. The heat evolved or absorbed during the phase change does not change the temperature and is therefore called latent heat. If the further termed as latent heat of melting, latent heat of vaporization, etc., depending on the nature of the process involved. In general, if delta LH is the latent heat and T is the temperature at which the changes of phase occur, the entropy change accompanying the phase change will be given by ds is equal to delta LH divided by T. The entropy change ds is termed as entropy of melting, entropy of vaporization, etc., depending on the nature of the process. For example, we have entropy of melting or fusion. Delta SF is equal to delta fusion H divided by TF, where delta F fusion H is the latent heat of fusion melting and TF is the melting fusion temperature. Entropy of vaporization. Delta SV is equal to delta vaporization H divided by TB, where delta vaporization H is the latent heat of vaporization and TB is the boiling temperature. It may be mentioned here that processes like melting and evaporation involve absorption of heat, which is taken as a positive by the convention of sign. Therefore, delta S for these processes is positive, is that these processes are accompanied by increase of entropy. On the other hand, the reverse processes like freezing and condensation involve evaluation of heat, which is taken as negative. Therefore, for this processes delta S is negative, is that these processes are accompanied by decrease of entropy. It may be remembered as discussed earlier that if heat is measured in calories, the unit of entropy change are calorie per degree per mole. If it is measured in joule, the entropy will be joule per degree per moles. Entropy change on mixing of ideal gas. Suppose at constant temperature and one number of mole of an ideal gas 1 at initial pressure P1 naught are mixed with N2 mole of another ideal gas 2 which had initial pressure P2 naught. Suppose after mixing their partial pressure is in the mixture are P1 and P2 respectively. Now we know that at constant temperature, the entropy change of an ideal gas when its pressure changes from initial state Pi to final pressure Pf is given by delta S is equal to R ln of Pi divided by Pf mole inverse. Entropy change of the first gas when the pressure of N1 mole of the gas changes from P1 naught to P1 is given by delta S1 is equal to N1 R ln of P1 naught divided by P1, that is equation 1. Similarly, entropy change of the second gas when pressure of N2 moles of the gas changes from P2 naught to P2 is given by delta S2 is equal to N2 R ln of P2 naught divided by P2, that is equation 2. Total entropy change on mixing the two gases will be delta S mixing is equal to N1 R ln of P1 naught divided by P1 plus N2 R ln of P2 naught divided by P2, that is equation 3. If P is the total pressure of the mixture, is that P is equal to P1 plus P2 and X1 and X2 are the mole fraction of gas 1 and 2 in the mixture, then the Dalton law of partial pressure P1 is equal to x1p and P2 is equal to x2p. Substituting this value in equation 3, we get delta S mixing is equal to N1R ln of P1 naught divided by x1p plus N2R ln of P2 naught divided by x2p, that is equation 4. Taking the simplest case in which each gas is taken at the same initial pressure and after mixing, volume of the mixture is the sum of their initial volume, is that V is equal to V1 plus V2. The final pressure of the mixture will be nearly same as initial pressure of each gas is that P1 naught is equal to P2 naught is equal to P. Then equation 4 is simplified to the form delta S mixing is equal to minus N1R ln of x1 minus N2R ln of x2, or delta S mixing is equal to minus R bracket N1 ln of x1 plus N2 ln of x2 bracket close. For a mixture of a number of ideal gas, equation 5 can be generalized to the form delta S mixing is equal to minus R summation of Ni ln of Xi. To calculate the entropy change for 1 mole of the mixture, divide equation 5 by N1 plus N2. We get delta S mixing is equal to minus R N1 divided by N1 plus N2 ln of x1 plus N2 divided by N1 plus N2 ln of x2, or delta S mixing is equal to minus R x1 ln of x1 plus x2 ln of x2, that is equation 7, which can be generalized to the form delta S mixing is equal to minus R summation of xi ln of xi, that is equation 8. From the above equation, we may conclude that ds mixing is independent of temperature. As xi is less than 0, delta S mixing will always be positive, is that mixing of gases is accompanied by increase in entropy. Physical significance of entropy is that measure of disorder. An examination of the various processes which are accompanied by a net increase of entropy shows that they are associated with an increased randomness of distribution. For example, first one is the melting of a solid is accompanied by a net increase of entropy as already discussed, and at the same time we know that the molecule, atoms or ion in a solid have fixed position and then become free to move about in the molten state. This is expressed by saying that there is no disorder among the molecules, atoms or ion in the solid, but the disorder set in which the solid changes into liquid. In other words, it is stated that randomness has increased. Second is the vaporization of liquid is accompanied by a net increase of entropy as already discussed, and at the same time the disorder or the randomness also increases because the molecule of vapors are more random than the molecules in the liquid. Third is heating a magnetized iron needle demagnetize it because the molecule of the magnetized iron needle which were oriented in a particular fashion lost the order on heating and becomes disorder, is that randomness increases. All spontaneous processes like diffusion of gas, flow of heat from the hot end to the cold end of an iron bar are accompanied by a net increase of entropy as well as an increase of randomness or disorder. For example, in the phenomenon of diffusion, the two gases which are separated initially get mixed up in a random manner. Similarly, in the flow of heat, the electron present on the hot end and having higher kinetic energy rush to the cold end, thereby making the distribution more random. Hence, it may be concluded that entropy is a measure of randomness or disorder of the system. This concept may be further understood with the help of the following example. For example, in a college, when all classes are being held, all the students are sitting in their respective class and rooms, and the disorder is minimum. As soon as the bell goes, the student of different classes comes out to go to the other rooms and thus get mixed up. In other words, the disorder or the randomness increases. Second is in the game of hockey or football, to start with, all the players take up some definite position and thus are said to be in order. As soon as the game starts, the players start running and thus they are said to have an increased randomness, which increases further as the game catches more and more momentum. Thank you.